Thank you very much. Thank you very much for introduction. And my name is Hansu Lee. I'm actually Korean, but working in Japan more than 10 years. Then my major is about air-sea interaction, actually. During my PhD and postdoc, I was focusing on the air-sea interaction, especially looking at the role of wave-breaking phenomena in the air-sea interactions processes. But today, when I was invited, I was thinking about some little different talks, the urban heat island. So this one is just, somehow even new to me, but I started this project. I was joining this project 6 years ago. This is our PhD students, and they are my colleagues from architect department. They invited me to join this project because I was focusing on atmospheric processes also. So they asked me to join and then try to do the regional climate modeling, and then assess how much the urban climate and how much the urban heat island will increase during the urbanization processes. So today I'd like to talk about the impacts assessment, the quantitative assessment of the land use change and the global warming effect on urban heat island in Hanoi, especially the Hanoi city in Vietnam, by dynamically downscaled climate modeling. So they are my colleagues. This is the product of the co-workers. Then this is our co-workers, the colleagues in Vietnam Institute of Urban and Rural Planning and under the Ministry of Construction. They are responsible for the urban planning in the Hanoi cities. So first, thank you for inviting me. This is the first time to Mexico City, and then I'm quite sleepy now. It's like a 12 hours differences between. If I get slower, please be understand, okay? I may lose my concentration during the talk. So the outline of today's talk is about, I just give you the background and the research purpose and methodology, and then results in terms of the land use changes, impact on urban heat island, also global warming impact, and then mitigation strategies, how to reduce the urban heat island in Hanoi city. And then also we are doing similar case studies for other cities in the ASEAN, Southeast Asia. So, and then finally I will give you some summaries. So what is urban heat island? This urban heat island is the urban areas with the significantly warmer than the surrounding areas, and then resulting from the urban and the rural energy balance differences. So if we look at the energy balances, we have incoming short and long wave radiations, and then also outgoing long and short wave radiations. These are the balanced, this is radiation balance equations. And then if you look at the urban energy balance equation, we have some heat emissions from the anthropogenic activities, from the buildings or car and the transportation. So we emit the heat, so we have to consider the anthropogenic energy heat releases in the energy balance in the urban scale. Also, they are balanced with the sensible and latent heat flux. Also, the energy is stored in the subsurface or in the building materials. They are storing the energy, heat. Also, the advective heat fluxes are occurring in the urban scale. So we have to consider those energies to consider the whole balances, energy balance in the urban scale. So if you consider the land use changes from the natural conditions to the urban, the concrete surfaces, then we reduce the surfaces for the latent heat flux releasing. The latent flux phase changes from water to gas, liquid to the gas, and then they release in the same temperature. Then they need the energies to change, phase changes. Then during that processes, the temperature energy is released to the atmosphere. That is cooling effect. But we are losing the surface. Therefore, we are losing the latent heat flux is consequentially is reduced due to the urbanization. So that will cause the urban heat island, temperature increases in the urban scale. Also, at the same time, sensible heat flux are increased in the urban scale. The temperature changes also, they are depending on the materials, the heat capacity of the materials, and then temperature changes. Since the latent heat flux decreases, then temperature increases, and then therefore the sensible heat flux also increases in the urban scale. That causes the temperature increases in the urban. that is urban. That is finally causing the urban heat island. So this chart is like a temperature and then population changes from 1980 to 2010 in the Hanoi, Vietnam city. Hanoi city in the Vietnam. Then the temperature, one is measured in the urban center, and then two are, sorry, this is a rural. Two are observed in the rural areas. As you see, by the definition, there are some temperature differences between rural and urban. 0.3 degrees in 1980s, and then now in 2010, at the time of when we start the project, the temperature difference is increased to 0.5. So Hanoi is already experiencing the urban heat island. So urbanization rate in terms of the population growth was 30% at that time. What happened here is like that they expand the metropolitan administrative district, so the population suddenly increases. But anyway, they are gradually increasing. So urbanization rate is about 30%. So this kind of urban development happened in many places in the Southeast Asian countries, like Indonesia, Malaysia, Philippines, Singapore, Thailand, and Vietnam. Like Jakarta is the capital city of Vietnam. Currently, it's like a population is 9.2 million, and then under the master plan, which is the urban development plan, they try to increase the population up to 12.5 million. The target is until the 2030s. Then the other cities propose quite similar master plans. Like the Hanoi city, for example, the target case studies of these cities of this study, the current population is 6.7 million. But the local governments, they proposed the master plan, Hanoi master plan 2030, and then under the master plan, they try to accommodate 9.2 million people by the 2030. So, so actually, this is the Hanoi, the map of the Hanoi metropolitan district. This is current situation, and then this is under the master plan situation. So this is like all the cities there, and then the red river is flowing from west to east. But under the master plan, they will expand the cities quite big to the left, and then to the west, and then to the north of the river, and even to the east of the river. So they designed satellite cities here and there and here, etc. So this is also the current status, and then this is a master plan of the Johor Bahru city of the Malaysia, the second largest city in the Malaysia. So they call it Iskandar Malaysia CDP. Then this is under the master plan. They will accommodate almost two times larger population by 2025. So, but we have been going through this kind of master plan, but in the master plan, we could not find any kind of scientific evidences or what kind of studies about urban heat island. They only designed the urban master plan like a designing aspect, without any scientific evidences or background about how the urban environment will change after implementing this master plan, how the urban heat island will increase, how the urban temperature will increase, or how the environmental, like transportations or the waste management, especially South Asian cities are suffering many environmental problems from the waste. So that kind of aspect is not really well investigated during the master plan. So we try to do the studies, especially perform the studies, especially about the urban heat island. For example, what happens if the target population is increased to the 9.2 million in the Hanoi city by 2030s, and then how much the temperature will rise due to the land use changes. Also, in addition, how much the temperature will rise due to the global warming effect. So we want to know quantitatively how much the temperature will rise by the regional climate modeling. So that was the starting point of the study, and then also try to found the scientific evidences and then give the feedback to the master plan. Master plan, every 5 years they revise the master plan, so we try to give some scientific evidence or information and then try to propose the mitigation measures to the urban heat island. So that was the background of our study. So research question we have is how much temperature will be increased due to the land use changes, and how much energy will be additionally required, and especially for cooling. As I said, this project was also, I have a collaboration with the architect people, and they are more focusing on the building scale countermeasures. So, if the urban temperature will rise by certain degrees, then that will increase the cooling load more increased. In the South Asian tropical region, the temperature and humidity is very high. They normally use the air conditioning system even at night time. That is causing the large consumption of energy. So if the temperature rises in the outside, then they will use more energies for cooling for the indoor life. So the architect people, they try to simulate how much cooling load will increase due to the temperature increase in the outdoor. So that is also one of our purpose. And then finally, how to minimize the U.S. urban heat island impact in the future. And then so the objective is that to assess the changes in urban heat island due to land use changes, also to examine the impact of global warming to urban heat island in the future, urban climate, also propose the mitigation measures for the urban heat island, and to assess the cooling effect and the effectiveness of urban heat island mitigation strategies. But in this talk, I'm not going to talk about this kind of cool energy consumption and then cooling load, etc. This is more out of my scope and then subject. So, how many of you know do you know where the Vietnam is? Sure. Yesterday I asked some students, but they doesn't know it. So here you have Mexico almost in the same latitude. They are located in the same latitude, and then here is the Vietnam. They have borders to the China in the north, and then to the west, Laos, Cambodia. Also, we have Thailand, and then this is China. Also, they facing to the South China Sea to the west, to the east. Also, here is Malaysia. If you go further south, you have Singapore and Indonesia. So they are in the Indochina Peninsula, and then they are all the Southeast Asian countries. And then here is the Hanoi city. Hanoi city is the capital city, but it's the second largest one. The largest city of the Vietnam is located in here, South Ho Chi Minh City. So this is the capital, Hanoi city. This is here we have a Red River, quite big rivers flowing from west to east. And then actually the Hanoi city is developed under the delta, Red River Delta. So quite high and flat land and fertile plain. So actually there are so many small lakes formed by the river a long time ago. So they sometimes call it city of lakes. The more than, I think, 100 lakes still remain in the current time. So this is a current urban areas. That's the oldest town and the old city is located here, and then this is the West Lake. They say West Lake, the old city, and then an existing urban area. We call it the existing urban area. This is the road connection from the airport is here. So then these are the all irrigated crop land, agricultural land. Then here, this is the current condition. The current means that at the time of 2010, when we started the project. So the population at that time was 6.7 million. Then this is the Hanoi city areas. And then under the master plan, the local governments tried to increase the population by 2.9 million by 2030, and even 10.8 million by 2050. And then these are the urban area, existing urban area, and then these are the new planned urban areas. This is the urban expanded to the north of the river and even to the east part of the river. Also, they designed the satellite cities, small cities here. Also, they designed the green belt between the existing and the new urban, and then also green buffer zones between the new urban and satellite cities. Even they put the green corridor. Within the new urban areas, there are some green corridor, 1, 2, I think 3, 4 green corridor. But for the design of a green corridor or green belt and green spaces, they didn't consider about this kind of scientific studies, just in the design aspect, the corridor That's like green buffer and green belt, etc. So master plan proposed a series of green walks and green belt, these kind of things. So in this study, the first part, we just investigate the impact of land use changes on urban heat island. The second part, we investigate the influence of global warming in the urban heat island. And the third part, we try to investigate what could be the mitigation measures to the urban heat island. Then the next part, the architect colleagues, they are doing some impact of indoor thermal comfort and the cooling load by the urban heat island. But today, I'm not talking about this one. So for the regional climate modeling, I use the WRF. Probably you know very well about the WRF. And then to learn the WRF, use the WRF, we need some input data, which are terrestrial data, also the global GCM data for initial and boundary conditions. Also, we need sometimes observed data for data simulation, and then we do the interpolation from the grid, GCM grid to the pressure grid interpolation, and then we learn the WRF when we do the post-processing. In our post-processing, we normally use the GLASS software, this process. Also, these are the characteristics of the WRF. But the WRF modeling is quite complicated and then quite sensitive to the physical parameterizations. So the physical parameters, including the cumulus schemes, cumulus cloud scheme, and the microphysics for cloud and the precipitation forming, and the radiation schemes for short wave, long wave, radiation turbulence, and the PBL schemes, and surface layer scheme, surface models. Then also initial and boundary conditions quite critical in the regional climate or RAF modeling. So I will show you some sensitive analysis. First, the first part, the impact of land use changes. These are the domain settings for the Hanoi urban heat island simulation. We set up the 3 nesting domains from domain 1 to domain 4. The grid resolution is from 27 to 1 kilometers, from domain 1 to 4 respectively. They are the physical parameterization. Also, the third domain and the fourth domain that has a quite high resolution. And then the default USGS data set, the land use cover data set provided by the USGS data set is not really good enough for the small and high resolution scale simulation. Especially if you look at the LULC data set from the USGS, for the urban area, it's almost it's not good at all. They are sometimes all considered as all the same categories, or even to the forest areas. So real configuration of the urban city is not really well considered in this data set. So we made our own LULC data set for the domain 3 and domain 4. For domain 3, we use this data set, global land cover data sets, 30 arcsecond. And so for the fourth domain, we use the ALOSA Avenir 2 satellite image data set, also combined with the master plan digital data set provided by the Vietnamese Institute. Then we have performed the sensitivity analysis, especially in terms of physical parameterization, focusing on the planetary boundary layer and microphysics, and then cumulus schemes. Then we tested more than 5 cases, and then these are the statistics by comparing the WRF output with the 30 years observed temperature data sets from the data you saw in the previous slide. Then we perform the modeling. These are the domains. These are the second domain, third domain, and the fourth domain. Fourth domain is like that. This one just covering the whole metropolitan of Hanoi City. And then this is for the current condition. We have only the old, we call it existing urban area in this study. And then this is another case study 2.1. Under the master plan condition, we have the new urban area. Also green belt, and then green buffer, and then even green corridors were created according to the master plan. So also we consider we performed the 1 month simulation for June 2013. This is we investigated 30 years past historical temperature record, and then we calculated the mean temperature for June. June is the highest, the summer seasons with the highest temperature in Hanoi city. So we calculate the mean temperature of the June. Then we pick up this month is quite very close to the mean climate of the Hanoi season. So we simulated the 1 month, June 2013, and then with this NCEP final analysis data set for initial and boundary conditions. This is the nighttime temperature distribution, and then these arrows indicating the wind directions. This is from the result for the current condition and the result from the master plan conditions. Wind directions is not much change, but if you look at the temperature distribution over the existing urban and the new urban areas, they have a higher temperature than this older current situations at nighttime. This is a daytime temperature. So at 2 p.m., then this is the temperature higher. We can find the higher temperature spots over the existing urban areas, and then we can find the hot spots, large hot spots over the even new urban areas, and even the satellite cities here and here. We have a new hot spots in the satellite cities as well. So then this one is showing the distribution of average air temperatures in different land use categories. We have these are the upper panel shows the average air temperatures percentage for daytime. This low panel showing the nighttime. Then we divide these air temperatures in terms of the same degree of the surface temperature, and then their percentages in the whole domain. Then if you look at this one, left column indicating the current situation, and the right column indicating the master plan condition. If you look at the current conditions, even during day and nighttime, most of the high temperature or the occupied by the irrigated crop land, because the surrounding land are the all crop land, agricultural land. But if you look at the result from under the master plan conditions, you can see the irrigated crop land, the proportions of the irrigated crop land are reduced dramatically, and then meanwhile, we have built-up areas, built-up land categories, their proportion are increased dramatically. And then if you look at this, the peak temperature, it was like 37.5 degrees Celsius in the current condition, but peak temperature is shifted to 38 degrees Celsius. And then we can imagine these are the kind of hot spots, the points with the high temperatures. So we can imagine that the hot spot, for example, with the 38 degrees Celsius, in the current condition was increased to 33% under the master plan conditions. Many places representing the high temperatures, which means they are hot spot. We call hot spot. So then, if you look at the nighttime, also before the master plan, most of the land occupied by the crop land. But after the master plan, in the master plan conditions, the crop land proportion is decreases, and then the proportion of the built-up areas increase dramatically, and then hot spot also with the 30, for example, 30.5 degrees Celsius increase 23%. So these are the special distribution of air temperatures, difference between current and master condition. This for the nighttime, this for the daytime. The difference is that the daytime is not really significant compared to the nighttime. There are some hot spots, then some large differences like between 1 and 1.5 degrees Celsius in the northern part of the Red River. But if you look at nighttime, almost all new urban areas showing the large temperature differences between the current and the master plan condition. So this one is showing the diurnal temperature changes for a day. It's like we calculated the whole average temperatures for the whole regions, and then showing the average changes of the temperature changes, diurnal changes from midnight to the midnight. Then the black indicating the current condition, and then the red line indicating the master plan condition. So after we implement the master plan, the nighttime temperature increases the average increases averagely 0.3 degrees, and then averagely during the night daytime the temperature increases 0.6. And then if we look at the only new urban areas, since the land cover is changed from cropland to the built-up areas, so then that causes the latent heat flux decreases, then temperature increases was 0.9, nearly 1 degree Celsius. This is average values. The maximum is almost reached to the 2 degrees Celsius. So as I said in the beginning, urban heat island is quite related to the heat budget, and then especially sensible and latent heat flux. So we investigated the sensible and latent heat flux for the whole domain, fourth domain. And then this black line indicates total energy budget, sensible heat flux at the current condition. And after we implement the master plan, the sensible heat flux increased not so much, but overall, even at night and daytime, they increase. But the changes in latent heat flux is much more significant than sensible heat flux. You can see the latent heat flux is much more reduced during the daytime. That means it loses the cooling effect due to the latent, evapotranspiration processes from the plants. So that will consequentially increase the temperature of the urban area. So the summary of the first part is like daytime peak air temperature remains at almost same levels, approximately 0.5 to 1 degree higher at maximum, even after the implementation of the master plan. The high air temperature areas would expand widely over the planned built-up areas, and then large green spaces proposed in Hanoi master plan are not necessarily effective at cooling all of the built-up areas. The significant reduction in latent heat fluxes appeared after the implementation of the master plan. It's somehow obvious results. So the next part, we investigate the impact of global warming on the urban heat island. So we use the downscaling, dynamical downscaling. There are two types of downscaling, statistical and dynamical downscaling. Then we use the dynamic downscaling. Simply, we downscale the global climate model results to the local regions by using regional climate models. And then simply like that, if we have a global climate GCM output, then we use the GCM output for the global regional climate modeling in the downscale for the interested areas. So at least we need 6 weather elements to learn the model. Then there are also, I think, some people are using the pseudo global warming effect or modeling, downscaling, that is like using the 6 element, but they are not using the GCM output directly, but only they use the current climate conditions, but simply increase the temperatures or other factors as you like. So imagine temperature will increase 1 degree Celsius or 2 degrees Celsius in the future condition, and then learn the models. That is sometimes called pseudo global warming modeling. But in this study, we use the direct dynamical modeling approaches. Then for the future prediction of the Hanoi urban climate, there are 4 scenarios, representative concentration pathways are available, of course, from the IPCC AR5 report, but we just consider RCP 4.5 and 8.5 scenarios. The RCP 4.5 scenarios, this is 2.5, 4.5, 6 is like the possible radiative forcing ranges. So this, like 4.5 means radiative forcing will be increased 4.5 watt per square meters from the current condition. And then if we think about the scenario in terms of CO2 emissions, under the RCP 4.5 scenarios, the CO2 emission will increase until around approximately 2040, and then will be decline. And then under the RCP 8.5 scenarios, that the CO2 concentration keep increasing, and then after 2080, then they will be stabilized. That is RCP scenario. And then in our simulations, we consider the only RCP 4.5 and 8.5 scenarios for the future Hanoi urban climate. So there are actually, if you look at the CIMI5 data set, there are so many GCM model outputs actually available, but to use them as a initial and boundary condition for the regional climate models, we need at least 6 variables. We need 6 weather elements, as I showed, needed to run the regional climate model. So we narrow down the GCM outputs, which have the all 6 elements in the data set. And then there were 38 models available. No, more than 38 data are available, GCM output. Also, we narrow down the GCM outputs, which has the all prediction result for RCP 8.5 and 4.5. They were like a 38 models. So before RCM modeling, we investigated how the future climate will be over the Hanoi regions. We defined this square as a Hanoi regions, and then we calculated the 38 ensemble means for the Hanoi region only. Then if you look at, these are the mean value, and then these dotted lines indicating the 5th and 95th percentiles. So if you look at the differences between the 2 scenarios, there are not much differences until 2050. And then some significant differences are occurring after 2050. Then we also invest, because practically it's quite difficult to perform the whole prediction modeling with the RCM. So we try to narrow down further, which what GCM is more suitable for the Hanoi regions. This is the black line indicating the mean values for RCP 8.5 and RCP 4.5. And then these 5 GCM outputs are plotted as a dotted line with the different colors. And then we found that MIROC 5, this is one of the GCM output, is quite close to the mean value of over the Hanoi regions for both scenarios. So we just decide to use this MIROC 5 GCM outputs for the initial and boundary conditions for the RCM modeling. Then, because the master plan was proposed for the 2030, we decide to simulate for 10 years from 2025 to 2026 to 2035, 10 years. And then we try to average the monthly temperatures for each June for a year. So these are the simulation scenarios for the global warming effect. First of all, we also perform the same current condition and the master plan conditions for June 2013 with the same NCEP final analysis data set. Then further, we calculated the global, we do the RCM modeling with the MIROC 5 data set, with MIROC 5 GCM output for the initial and boundary conditions. And then for the 10 years, 2026 to 2035. These are the configuration of the model and then physical parameterizations. And then these are the results. So these results indicate the upper panel indicating the spatial distribution average air temperatures from current master plan condition, and then RCP 4.5 scenario and RCP 8.5 scenario conditions. So you can see, as we see in the previous slide, after implementing the master plan, we have temperature increases in the existing and new urban areas at the nighttime. And then if we compare these two, for example, then the effect of global warming is obviously observed over the whole domain. So especially upper part, temperature increases dramatically compared to the land use change conditions. So between the two scenarios, RCP 4.5 and RCP 8.5, the temperature change is not really significant, actually. There are some detailed changes, but the degrees, magnitude of the changes are not really significant. This lower panel shows the temperature distribution, average air temperature distribution at the daytime for the current and the master plan condition. You can see the over the whole new urban areas, temperature increases. And then by comparing these two, we can see the impact of global warming. So this one, over the whole domains, we have temperature increases, especially the northern part, temperatures are increased. We think they are mainly due to the wind. The main wind direction is from the south, so the northern part, the temperature increases much more than the southern part. Then between the two, also in the daytime, it's not really significant between the two scenarios. So this one is showing the statistical summaries. The minimum, maximum, and the 25 and 75th percentiles, and then these are the median of the temperatures for each year from 2026 to 2035. And then the rightmost bars are indicating the means for the 10 years. So the minimum and maximum values of the mean, these 10 years mean values, and then median as well. And so this one, upper panel indicating the results for all existing urban areas, and then lower panel indicating the new urban areas, and the left column indicating the result for RCP 4.5, the right column indicating the result for RCP 8.5. So interesting to me is that if you look at the results for under the RCP 4.5 scenarios, we can see the interannual, there are some higher values, but we can see the interannual variability of the climate in the urban, over the urban, Hanoi urban areas in the future. But under the RCP 8.5 scenarios, that such kind of interannual variability is not well appears. So I interpret that this current climate conditions could not be maintained under the higher concentration scenarios. And then if we look at compare the existing and the new urban areas, the median values, this is in the new urban areas higher than the existing urban areas. And then if we compare the median values between the two scenarios, as we see in the previous slide, the difference is not really significant. So this is actually a summary of the 10 years RCM modeling. That there's a diurnal variation of the average air temperatures for the fourth domain, whole domain. So by implementing the master plan from the current conditions, the temperature increases at nighttime is about 0.3 degrees, and then daytime 0.6 degrees due to the land use changes. But by the global warming, from the RCM modeling, the nighttime temperature increases about 1.1 degrees Celsius, so approximately, and then this is at the daytime is 1.4 degrees Celsius. In the new urban areas, the global warming impact on the urban heat island is like 1.6 degrees Celsius, and then also daytime is like 1.4 degrees Celsius. If we look at the differences between two scenarios, it's not really significant, but yeah, RCP 8.5 produced a little bit higher result than the 4.5 results. So the peak air temperature in Hanoi existing urban area will rise about 2.5. These are the average. Peak is 2.5 degrees Celsius by 2030, and 71% of the increased temperature of existing urban areas is attributed to the global warming effect, much more rather than the effect of land use changes. So the summary for the global warming effect on urban heat island is that the land use changes proposed in the master plan are expected to increase the average air temperature in the existing and the new urban areas by up to 0.6 and 1 degree Celsius, respectively. And the urban air temperature was expected to increase along with the global warming. Then the projected increase of the average air temperature was up to 2.1 degrees Celsius in the existing urban, attributed to global warming, 1.5 degree, and then also attribute to the land use changes approximately 0.6 degrees Celsius. So global warming contributed at most 71% of the temperature increases in existing urban areas of the Hanoi city in 2030s. But as you see, that this is based on the result of one downscale modeling using the one GCM output from MEROC 5. So of course, it's more recommended to do more RCM modeling to account the wide range of the climate variability as uncertainties for the future climate. So, and then next step, we try to see or investigate the mitigation measures for the urban heat island. So, in many urban heat island related researchers are proposed various measures depending on the spatial scale, also depending on the causes of the urban heat island. So as you see, the urban heat island is due to mainly the urban and rural energy balance differences, and then they are caused by land use changes. Also, some additional heat released from the anthropogenic activities in the urban areas. Also, as a countermeasures, we see that wind blowing and the ventilation effect is very, very important in the even city and the building scale. So there could be the measures for depending on the causes, and then depending on the scale, there are various countermeasures. But in our scale, our study only consider the kind of urban scale measures, approaches in the urban planning scale, etc. That could be used the urban planning procedures. So these are like urban green areas. The photos of urban green areas. This is also photos for the equally distributed urban planning. And then this is showing the green walls and then green roof. So using some special painting materials, then to increase the albedo of the roof, so you can use the reduce down the cooling load of in the building scale. This is urban scale, and the building scale also it's a building scale. This kind of also my colleagues are working on the kind of new materials, painting materials to increase the albedo of the buildings, etc. So this is how the old existing urban area looks like in the Hanoi cities. It's packed of houses. They're like 4-story houses. One family using the 4-story house. They are all detached houses. Then this is the look of the old urban areas. There is no places for the green spaces anymore, as long as you collapse down some buildings. But this is how the new urban looks like. The new urban construction is going on. I took this that in the highest building in the Hanoi city, the new urban areas, and there's each blocks and has some kind of small amount of greens surrounding, and then high-rise buildings. So as first step to investigate what could be the countermeasures for the urban heat island is that we simply see the effect of proposed green spaces in the master plan. So simply we remove the green belt in the master plan, and even we remove the green buffer and connect the new urban to the and then satellite cities with the whole as a green areas. Even we remove the every green spaces. Simply see their effect by the regional climate simulations. So also when we convert this green area into the red area, for example, we did not completely change from green space to the building, but in the WAF function, there is a function of urban fraction that so we can even consider the fractions of the built-up area and the vegetation areas within one grid cells. So depending on the urban fractions, these kind of components could be considered in the calculation. So when we convert the green, for example, green spaces into the built-up areas, we still remain in the 20% of the vegetation and within our green, one grid cells. So 80% of grid cells we assume that change it to the built-up areas. So we performed 4 simulations. Then we choose this one. This month is the hottest month during the 30 years, the June. See how temperature could rise, to see how much temperature will rise. Then this is the temperature profile, cross sections, temperature profile along this cross section, east-west cross section. Then these bars indicating the land use categories. So for example, here we have a Red River, This one is Red River here, Red River, and the temperature is dropped, surface temperature is dropped. The wind speed is not that strong. Then during daytime, mainly the wind direction is, the wind is blowing from the west. Then here we have also Red River, so temperature is rising. And then due to we have a mountain, and then the temperature decreases, and then temperature gradually increases. Then the SC1 indicating the result from master plan condition, and then SC4 indicating the scenarios without any green spaces. We remove the all green spaces. So by removing the all green spaces, or if you look at the temperatures over the green spaces, before removing the all spaces, temperature decreases due to the green spaces. Here, after removing the all green spaces, temperature should keep rising. Then the effect of the green spaces is like 1 or 1.5 degrees Celsius at the daytime. During the nighttime, you can see the larger effect of the green spaces than the daytime. Then the westerly, mainly the wind direction over this, there is a mountainous areas, and then the main wind is at the nighttime is blowing from the south. And then some wind is blowing from the west, but not so strong. Then you can see the temperature decreases over the green spaces, and then they are like more than 2 degrees Celsius. Then this one is showing the temperature and the wind profile along this north and south section. Then these are also the land use categories. Then over the rivers, water bodies, the temperature drops. And then this one is the main wind direction is the westerly direction from here. So then also here, at nighttime, the wind is blows from the south-north direction in this direction. You can see the wind is blowing, then from the south to north, and then the wind effect, temperature gradually increasing from the south to north due to the wind ventilation effect. Then here, during nighttime, the effect of the green space is larger than the daytime. So reach more than 2 degrees Celsius in the southern part. So simply, as a next step, we try to see this. It's like this is the proposed green spaces in the master plan, green buffer and green belt and then green corridor. Then we try to keep the total volume of green space as the same, as constant, but we simply equally distributed green spaces over the urban ring. This is like quite an ideal situation. It's, as you can imagine, it's impossible to implement it. But we try to see, we try to investigate whether this kind of study was done or not in the urban heat island aspect, but we could not find a quantitative assessment of this kind of equally green spaces effect on urban heat island. That's why we try to simulate and see how this equally green space, distributed green space effect will be on urban heat island. Then here, the green spaces, the green space category is mixed shrubland and grasslands, and then we even change the mixed shrub and grassland into the mixed forest categories in the urban areas, and then see the differences. Also, while we are changing the color from red to green, from build up area to the green, we also try to keep up. Maintain the 20% areas still as a built up, and then change the rest of 80% into the green spaces. Then this is the result. This is a daytime result for the master plan condition, and then this is green belt with the mixed change the category into the mixed forest. Then this equally distributed green spaces, and then equally distributed green spaces with mixed forests. As you see, if we change the green the land use categories into the from grassland to the mixed forest, their effect is much. The effect on urban heat island mitigation is larger than the original land use categories. If you look at the green, equally distributed green spaces, in this one, it's a little bit difficult to see their effect. But if you see this one, for example, by changing the land use categories from green grassland to the mixed forest, their effect is very significant. The cooling effect is expanding more to the peripheral areas of the park. For example, if they are the park, due to the also wind effect. So this one showing the spatial distribution of temperature only for the built-up areas. And then see the scenario 1 is the master plan, and the 5 is with mixed forest. And then 6, 7 is representing the equally distributed green spaces. This one is mixed with the green land use categories with the mixed forest. This one, by changing the green spaces, the spatial distribution is not much changed. This is the average one, but not much changed. But if we look at, so for example, the hotspots with the temperature 34 degrees Celsius, after we implement the equally distributed green spaces, hotspot reduced dramatically, almost 50% reduced with the temperature 34 degrees Celsius. So then at the daytime, also the hotspot with the temperature nearly 40 degrees Celsius, it decreased. The proportion of the hotspot decreased to 16%, 6.2% by implementing the equally distributed green spaces. So further, of course, the equally distributed green spaces is impossible to implement it. So we try to think how we implement those effects in the new urban master plan. So see, this is existing urban and new urban areas. Then for the existing urban areas, it's almost impossible to implement those kind of schemes. But for the new urban areas, as you see, there are still the construction is going on. Then we can somehow implement or increase the green spaces further. So here we define the green coverage ratios. And then in the master plan condition, there is no definition or no rules for the green coverage ratios. Only they are represented as building areas, built-up areas. So we just try to introduce this green coverage ratio 10%. So for each district or each blocks, 10% of the block should be the green spaces. Then, which means if you want to accommodate the same number of people, then building height will be increased, right? So that kind of things. Then see, we try to increase the green coverage ratio 30% for each district and then blocks. Then even we change the green species from grass and shrubland to the mixed forest, and then see their effect. So this is the distribution of the temperature in built-up land use, only for the built-up land use categories. For the existing urban areas, there's no significant changes. We cannot implement the new, then the effect of the green coverage ratio is not really significant for the new urban areas, existing urban areas, even for the night and daytimes. But for the new urban areas, the peak temperature is like the same. It's not really reduced as for the equally distributed green spaces. But if we look at the hotspot with a temperature like 30 degrees and then 30.5 degrees Celsius, the proportion of the hotspot decreases 13%. So we can see somehow the effect of green coverage ratios. And then considering the kind, we can somehow implement the equally distributed green spaces. This one, at the daytime, the peak temperature reduced from after implementing the green coverage ratios. So like the peak temperatures for the hotspot, this was 37.5 degrees Celsius, but after we implement the green coverage ratios, then the peak temperature for the hotspot decreased like 0.5 degrees Celsius. Then also the proportion was decreased to 33%. So this is a spatial distribution of temperature differences between master plan condition and the difference between the master plan condition and then the green coverage ratio 10%, 30%, and then 30% with the mixed forest. Of course, as we saw in the previous slide, there's not significant changes in the existing urban areas, but for the new urban areas, by implementing green coverage ratio and even change the land use to the mixed forest, we can see many temperature decreases compared to the only master plan conditions. This is nighttime and the daytime. So nighttime temperature the difference is much more significant than the daytime temperature differences. So, and then we try to investigate the other elements like temperature and relative humidity here, and then wind speed. The temperature, this is the averages for the whole domain. The new urban area. Then the temperature decreases after we implement the 30% green coverage ratios with the changes of land use categories into the mixed forest, like 0.52 degrees Celsius. But here we have some decreases, wind speed decreases in the nighttime. The overall they are slightly decreased, but here in nighttime wind speed decreases a little bit larger, but the magnitude is not that big. And also relative humidity is after we implement the green spaces, relative humidity increases. So we can imagine after we change the grassland into the mixed forest, then they disturb the wind ventilation effect. Also, they increase the humidities. So we have to consider those. But their magnitude is not that significant. So this is a summary cooling effect of the green spaces in Hanoi. And there's like a first one, the green strategies proposed in the master plan are not necessarily effective at cooling all over the built-up areas. So equally distributed green spaces show a better performance in the reduction of urban air temperatures, especially at night. Then nevertheless, the implementing the equally distributed green spaces is difficult in the real master plan. So we propose the green coverage ratio, and the improved green coverage ratio have the similar air temperature reduction as the equally distributed green spaces. Although the increase in green coverage ratio would not lower the peak air temperature, but it is effective to lower the number of hotspots as the green coverage ratio increases. Then greater reduction of the hotspots during the daytime and nighttime is achieved when the mixed forest is used as the vegetation cover, land use cover, and in the equally spaced in distributed green spaces. Nevertheless, trees in the green spaces should be carefully selected as they may block the wind blows and then increase also humidity in the urban areas. So I will go through very quickly environment in the cities. This is due to the increase of in the sensible heat and the reduction of the latent heat fluxes. And the anthropogenic heat releases give additional sensible heat to the urban environment, the transportation, and the building, cooling load, and the heating and cooling load from the buildings. And both factors result in the increase in air temperature, particularly at night. So UHI mitigation aims to reduce the sensible heat as much as possible, and while we maintain or try to increase the latent heat flux through the green spaces, etc. So global warming effect will cause considerable increases in urban areas temperature in the future, and then it contributes up to 71% of the increased temperature increase in the future Hanoi urban climate. So these are like a small schematic diagrams that we think how we consider the mitigation measures and also adaptation measures depending on the temporal scales, and then mainly focusing on the reductions of the causes of urban heat islands, like reduction of the latent. We try to reduce of the evaporative surface, increase the evaporative surface, and the surface try to improve the surface materials to reduce the sensible heat flux, and then also try to reduce the anthropogenic heat released to the atmosphere, etc. These are also the causes and the mitigation, the actions that we can take for the mitigation for long terms and for the short term short-term effect on the actions that we can take and control. And then for the building scale and for the urban scale, that kind of things. So, yeah, thank you very much. This is the end of my talk. Is this already time to finish, right? Yes. Then I skip many things, and then you can find most of the detailed things in our papers about this series of papers. Thank you very much. Yes.
Muchas gracias. Thank you for the talk. ¿Preguntas? ¿Se pueden hacer en español? ¿Tiene ahí un traductor?
Yeah, I can understand Spanish through the translation.
Thank you very much for your talk. It was very interesting. I have a question that is a little bit side question. I was surprised that in some of the maps that you presented for the surface temperature, although you were showing mainly the temperature changes between different scenarios, I was surprised that the river was so warm. The temperature in the river was so high, and well, not in this one. Before this one, the river temperature was low, but in the other one was the warmest. In the that one, the previous that one. So in case 2.2/2 and 2.3, it's very red, like 37, 38.
This color is in these ranges. This looks similar, but it's like purple.
In the ones in the right?
It also looks, it's in this range, it's not in the red colors. Sorry, the color range is looks similar, but this is a purple.
Okay. Okay. My question was if there is some air-river interaction in the model, because if you prescribe the river temperature or if you allow it to evolve. That was the question. Okay. But okay, this changes everything. Okay.
Yes.
Buenas tardes.
No.
Buenas tardes. Yeah. Claro, si Hanoi, desde el diseño urbano, es una ciudad compacta o difusa. Porque las ciudades difusas tienen también la presencia de mayor motorización y por ende eso pudiera ser una variable confusora para hablar del calentamiento global y de las temperaturas. Y si la apuesta para el 2030 del plan maestro que implica invertir la lógica, o sea, más zonas verdes y menos uso de la tierra para construcción, de una u otra manera no favorece más utilización de medios de transporte motorizados y vaya a generar vaya a afectar de una u otra manera el calentamiento. O sea, quiero saber si esto está pensado para una ciudad difusa o más para una ciudad compacta.
Oh. I'm sorry if I'm mistaken. Hanoi is like in terms of population, it's quite a big city, but in terms of spatial scale, I think it's like a compact city. For example, here, this is about 100 by 100 degrees. At 100 by 100 spatial the domain size. So it's like 100 kilometers by 100 kilometers. Yesterday I saw that city of Mexico is almost like the same size. But the city of Mexico spread is almost covering in this 100 by 100 kilometers. It's quite big compared to the Hanoi. The city of Mexico is much big in the spatial scale. So if we consider like 9 million, for example, by 2030, but this city size is like this amount. It's less than quarter of this domain. So compared to the city of Mexico, I can say compact city. But this is a relative conception. So yeah, of course. Then what was your narrative questions? Like, is that okay?
¿Más preguntas?
La voy a hacer en español. Muchas gracias por la presentación, interesante. ¿Hicieron algún análisis para el caso de la precipitación? Ya que corrieron el WRF, da N variables, pero no sé si hayan abordado esta otra variable que es, por supuesto, tiene un alto nivel de incertidumbre, como todos lo sabemos, pero bueno, si está la información ahí, ¿hicieron algún análisis al respecto?
In this study, since we are focusing on the urban heat island, we just see the temperature and the heat budget, the wind, etc. But we didn't see the precipitation in this simulation, in this study. But in my other studies, I'm actually quite interested in the hurricanes, the typhoon. We are always, every year we are facing the typhoon. That this year also we have three typhoons landfall already into Japan and Korea. So in my studies, other studies, typhoon simulation studies, I consider the rainfalls and then other factors. Then the rainfall simulation was not that bad. It was good, quite good actually in my other studies, not in this study. But.
Lo pregunté porque en el caso de la ciudad, de México está el efecto de la isla de calor que se ha medido a través de los registros históricos, pero también hay una correlación con precipitación, con la intensidad de la precipitación que se da en la ciudad por el efecto convectivo del aire o la humedad que viene del entorno de la ciudad y condensa, y entonces hay eventos de mayor intensidad de precipitación. Por eso preguntaba.
Sorry, I couldn't understand the beginning of your question. Okay, so like the correlation between temperature and the precipitation, right? So, that's okay? We can talk after the break, yeah.
Una pregunta, felicidades por tu presentación. ¿Tomaron en cuenta o están tomando en cuenta el tipo de vegetación con el que van a reforestar? O sea, van a metiendo mucha vegetación, pero ¿qué tipo de vegetación van a incluir? Porque hay muchos problemas, por ejemplo, aquí tenemos muchos problemas porque se han introducido muchas especies, muchos árboles, veo ahí también muchos pastos, muchas malezas, las cuales son muy alergénicas. Entonces, desde el punto de vista de salud, ahí hay que tomar mucho en cuenta eso, ¿no? No lo sé si tomaron en cuenta eso, pues.
Yeah, I agree with your comment, yes. Yeah, I completely agree with your comments. And then the species of the greeneries is very important, also from our studies. In the master plan, in the Hanoi master plan, the information was that thick, but we are looking for the whole master plan information. They didn't mention about the specific species of any greens, for the green spaces. They say only green spaces, that's all. No mention about species for the greenery. So for our studies, we can see even that by changing the green species, we can see the temperature decreases and increases in the even from the simulation. So our conclusion is that we have to carefully choose the species for the green spaces. So then by looking at the wind distribution, wind ventilation effect, also by looking at the temperature, by looking at the humidity and wind speed, the effect of the trees or species. So when you try to implement the green spaces, also we have to carefully choose the species for the green spaces. That's quite a good comment, yes.
Sí, sí, gracias.
Well, yes, when you say that you're expecting 30% increase, 53% increase is in urban area or is in population? That's the question. And the other is basically I think we have some different kind of mental framework. I don't know how much of the analysis is but you use plan and propose it. You never use the word expected. That plan, that master plan, they say the target population is that's millions. And that is a target or is it an expected based on population growth?
It's like expected, or yes. So I think it's sort of like expected is like a target. I don't know. It's quite difficult to differentiate, but yeah, it's like expected populations by the 2030s, and then yeah.
The tendency, let's say here in Mexico, we're never there to say plan.
Yes, in terms of population, yeah, plan is not the correct word for the in terms of population, but yeah, expected word. We cannot plan the populations. Yeah.
And the other, so in your personal opinion, how much of that percent of success of the master plan? You know, in developing countries there are plenty of plans and
success.
Very little success of that.
You mean that how much do I expect?
Yes, no. How much do you expect this master plan
to be success?
Yes.
Yeah, that's quite hard question. Even I also think it is quite difficult master plan. But when I visited the real site, I visited the real new urban site, and then really the construction is still going on. Then, so that Vietnamese government, when we first initiate this project, and then we didn't have any request or the contact from the local government. We did it. We initiated by ourselves. Then, after 2 years, we have some preliminary result, and then we brought our result to the local government, and then they was very interested. They were very interested in our research, and then they eager to see what could be the consequential of the master plan for the future urban climate or urban conditions. So then it's like about the green spaces, about green coverage ratios. Then they was also very interested on that kind of things. We just like say that it's better to propose, or there was no regulation or rules for the green coverage ratios, and then so it's better to specify that kind of green coverage ratios for the new urban areas, because it's beginning of the master plan, so we can implement it. New existing urban area is almost impossible. So that kind of thing, it's quite depending on the decision makers or local stakeholders, whether they really want to improve the situations. Then that master plan could be successful, or also depending on I think local stakeholders, local peoples, and then their willingness, I think, yes.
Gracias por la presentación. Una pregunta. ¿Existe en la ciudad de Hanoi algún umbral de temperatura en que la población sufra algún efecto por cuestión sanitaria? Si existe este umbral, por lo cual estén tan preocupados en este aumento de temperatura, porque independientemente de que va a haber un cambio en cuanto al confort de la población, si puede existir por cuestión de enfermedades.
Yeah, that's also good questions. Actually, I didn't present about the other issues, as health issues or heat stresses or health diseases related to the heat. also like dengue fevers or some kind of diseases that could be caused due to the temperature increases. Then my colleagues also investigate the relationship between temperature increases and the heat stresses, and then heat diseases like the dengue fevers and that kind of things. Also, if you go to these cities, it's really humid actually. If you go, there's only 2 seasons, wet and dry, or sometimes people say hot and very hot season. So if you go to the very hot season and wet season, the humidity is almost 99%. I couldn't believe it, but when I visited the site, normally the houses consist of 4-story buildings. They sleep in the 2nd floor. 4th floor is too hot, they cannot use it. And the ground floor is very humid. As you see, the city was built on delta area. So during the wet season, the groundwater level is increased very high. So a lot of humidity is coming from the land surface. So that causes a lot of unpleasant. The indoor thermal comfort is very bad, actually, not good at all. So they are doing the simulation, also investigating the indoor thermal comfort, and then how to improve the indoor ventilation, how to improve the thermal comfort in the indoor also as well. So my colleagues in the architecture department, they're doing that kind of researches also.
Thank you.
Ok, bueno, creo que ahorita damos por terminada la conferencia y le damos las gracias al doctor Lee Han-soo. Nada más les aviso.